In this video, I'm going to be introducing you to two of the fundamental concepts of calculus, which is the derivative and the integral. But in other terms, we're going to call those two things the tangent line problem and the area problem. This is from your textbook. The tangent line problem is concerned with finding a line that's tangent to an arbitrary curve on the coordinate plane. So like over here in this diagram, you can see that that line just touches the curve at point P. And it's the same kind of thing as a tangent line to a circle, where it just touches the circle at one point and nowhere else. That's what this problem is, and it's the first fundamental aspect of calculus that I'm going to introduce today. In order to find the tangent line, we're going to use limits, which I think you were introduced to last year. You're going to take the limit of a secant line as the 2 points that it passes through get closer and closer together. So on this page, you can see this formula here that says the slope of the secant line is equal to the difference quotient that you've been working with, which is dependent on the change in x, which is represented in this diagram right here, the distance in the x direction between these 2 points on the secant line. So as you take the limit of this, as the delta x goes to 0, you're left with a tangent line, as can be seen here. You can see the points getting closer and closer together, and the line between the points getting closer and closer to a tangent line. So just to make that more clear, I have a Desmos graph ready, so like I can show what's going on. Okay, so here you can see there's a red point and a blue point, and a secant line that passes through them. The problem here is we want to find the slope at the red point. Instantaneous slope, like at that very point on the curve, what is its slope? Which is equivalent to finding the tangent line. So right here we have this secant line, and if you reduce h, which is another word for delta x, it's used interchangeably, usually. If you reduce the distance between the blue and red points of the secant line, which is called h, you can see that the line gets closer and closer to a tangent at that point. You can move the point around, and it will continue to be a tangent. It goes from a secant line, you reduce h, and it goes to pretty close to a tangent line. And if you take the limit as h goes to 0, you'll get a perfect tangent line, which is represented by this, the derivative. This is a perfect tangent line at all points. And you can see here, I'm taking the m1 is the slope at x0, which is the x position of this point. I calculate that slope by taking the derivative of f of x, which is this curve, and evaluating it at x0. And then the tangent line is t of x right here. That's just the basic equation of a line, modified from the slope-intercept form. So that's the tangent line problem. And the other main concept I want to introduce here is the area problem, which is down here. This also uses limits. Everything in calculus pretty much uses limits. And this uses infinite sums too, which is also another limit. But the idea here is we want to find the area bounded between x equals a, x equals b, which are just two numbers, and then between some curve f of x and the x-axis, as shown with the shaded red region or pink region right here in figure 1.3. And to do this, we use something that we already know, which is the area of a rectangle. As you can see in this diagram, we're putting rectangles under the curve whose top left corner just touches the curve at that one point. And then you can add up the area of those rectangles, and you'll get an approximation to the area under the curve between those two x values. And you can take the limit of the size of the width of the rectangles. So they get narrower and narrower, and you get closer and closer to the area of the region. As you can see with this, these rectangles are smaller, and it's obviously closer to the actual area bounded by the curve and the x-axis. So I have another Desmos thing for this. It's the area problem. This is called a left Riemann sum. That doesn't really matter right now, but that's what it's called. So as you can see, we want to approximate the area between A and B, which, as you can see on the left here, is 0 and 5. So A equals 0, B equals 5. We want to know the area under x squared over 5 plus 1 between x equals 0 and x equals 5. So right now you see that there's only two rectangles. That's a pretty bad approximation. It's obviously an underestimate. There's lots of area that's not being accounted for. If you increase the number of rectangles, you can see that less and less white space is being left behind. So the approximation is getting better. And as you make the rectangles very small, it's a good approximation. And this is going to be pretty close to the actual area if you sum up all the areas of these rectangles. Now, I can't really make these rectangles any smaller, so it will get better because Desmos doesn't handle it right. But the idea is that you can make the rectangles arbitrarily small, and the limit of the area, the limit of the sum of the areas of these rectangles, when they are added together, will give you the area under the curve. And that's called an integral after you take the limit. And that is all.